Sangeeta Sharma, Associate Professor, Department of Chemistry, Government Dungar College, बीकानेर। आज हम MSc प्रीवियस पेपर 3 यूनिट 4 सरफेस केमिस्ट्री में केल्विन इक्वेशन पढ़ेंगे। The Clausius-Clapeyron equation is derived ignoring the effect of the interface. The Laplace-Young equations show that the surface effect becomes significant as the curvature of the surface becomes more pronounced. Therefore, the vapor pressure of the liquid droplet should not be expected to be the same as that of the bulk of liquid. Considered a case when a vapor liquid system with a planar interface is broken into large number of small droplets as shown in figure. The vapor pressure changes from P0 to PV and the pressure of the liquid changes from P0 to PL. The condition for reversible change is given in equation first. d mu L is equal to d mu V. This is equation first, where the subscript L and V denote the vapor and the liquid phase respectively. Since all other thermodynamic variables except pressure remain constant during the changes, we got from equation first integration P0 to PL dL dt is equal to integration P0 from P0 to PV dV dt. This is equation number 2. The left side of this equation 2 is written as integration from P0 to PL dL dt is equal to VL PL minus P0 is equal to VL PL minus PV plus VL V PV minus P0. This is equation 3. This shows that equation 2 may be written as VL PL minus PV is equal to integration from P0 to PV VV dt plus VL PV minus P0. This is equation 4. It should be seen that two terms of the right hand side involve the same pressure difference but volumes in different phases. Since the volume of the liquid is much smaller than that of the gas, we may ignore the second term on the right hand side. Now we integrate the first term on the right hand side and substituting the result on the Laplacian equation on the left hand side to get the following equation. Dl 2 gamma upon R is equal to integration RT upon P dP is equal to RT ln PV upon P0. This equation is known as Kelvin equation. This equation shows that as R decreases, the vapor pressure increases. The Kelvin equation points out the difficulties associated with the formation of a new phase. Suppose we start from a vapor phase and compress it to the saturation vapor pressure P0. Formation of the liquid phase requires molecules coming together and coalescing. It is quite unlikely that a very large number of molecules will come together at once to form a drop. It is more likely that a few molecules coalesce starting with a pair to form very tiny droplets. The Kelvin equations show that the equilibrium vapor pressure for such droplets is several times larger than that for the bulk liquid. So the droplets are likely to evaporate rather than come together to form the bulk liquid. From this analysis, we can conclude that the pressure has to be considerably large than the equilibrium vapor pressure of the bulk phase P0 before condensation can occur. In practice, condensation usually starts on dust particle or on surface sites on the wall of vessels. The presence of these sites for nucleation prevents supersaturation of the vapor phase. The Kelvin equation also shows why liquid becomes superheated before boiling. Consider a bubble of radius r inside the bulk of liquid. The pressure inside the bubble must be greater than that of the bulk liquid. The smaller the bubble, the greater the pressure. Therefore, there is a barrier for the formation of small bubbles which lead to the superheating of liquid. Violent pumping often ensures as spontaneous nucleation leads to bubbles big enough to survive to ensure smooth bubbling at the true boiling temperature. Nucleation centers such as small pieces of sharp edges glass or pumic stone or bubbles of air should be introduced. This is actually done in practice. Similar behavior is observed with the freezing of liquid and the crystallization of solute from the saturated solution. For example, extremely pure water may be cooled to minus 40 degrees before it brings to solidify. Even though the Kelvin equation is useful in solving the difficulties involved in phase transformation, but it cannot be used quantitatively. First, the surface tension depends on the radius of curvature, and for small radii, this dependence becomes very important. Therefore, one cannot use the Kelvin equation for droplets of every conceivable size. Second, macroscopic thermodynamics cannot be applied to systems such as a tiny droplet consisting of small number of molecules. Fluctuation from equilibrium becomes very important and should be incorporated into this theory. Now we take adsorption isotherm. Browner observed that instead of using pressure of gas as variable, we plot volume adsorbed in a ml at standard temperature and pressure per gram against P upon P0. Seven type of isotherm we get. Shape will depend on the adsorbate and the nature, pore structure, surface extent of adsorbent. Out of 7 types, 2 for non-wetting adsorbent system. These isotherms show the involvement of van der Waals forces. The first type of isotherm is typical isotherm at low pressure. The shape of the type first, second and fourth is similar. At very low pressure, the amount adsorbed is directly proportional to the pressure for almost all type of isotherm. In first type of isotherm, It's shown by low pressure and moderate temperature, and only monolayer is formed and which is became saturated. The second type of isotherm is shown by multi-layered absorption, and the point B indicates completion of monolayer, and then formation of multi-layer is started. In third isotherm, no transition between monolayer and multi-layer. It means monolayer and multi-layer formation started simultaneously. The fourth type of isotherm shows saturation of both monolayer and multi-layer. It is just similar to second type, but there is difference between second type and fourth type is, in second type the multi-layer saturation is not shown, but fourth type of isotherm shows the saturation point of multi-layer. The fifth type of isotherm shows that adsorption increases more rapidly with increase in pressure, and saturation attains saturation at very high pressure. At very low pressure, first, second and fourth became similar, amount not increase rapidly. At very low pressure, adsorbed amount is directly proportional to pressure for all types. Third type and fifth type of adsorption isotherm shows that amount adsorbed is increased rapidly. This table shows that type for isotherm is Langmuir isotherm, where monomolecular adsorption is there and E1 is equal to 0. And example of this isotherm is adsorption of oxygen and nitrogen on charcoal at low temperature at 78 degree Kelvin. The second type of adsorption isotherm is sigmoid type. It is for multimolecular, and E1 is less than E2. Adsorption of nitrogen on silica gel at 78 degree Kelvin is the example of sigmoid type. The third type is hyperbolic type. Weak force of unimolecular layer adsorption, E1 is greater than E2. Adsorption of bromine on silica gel at 194 K. Fourth type of adsorption isotherm is sharp approaches to the line P0. Multimolecular in capillary shape, E1 is less than E2. Adsorption of benzene on Fe2O3 gel. And fifth type of adsorption isotherm is elongated S shape, multimolecular in capillary shape. E1 is greater than E2. Adsorption of water vapor on charcoal at 373 Kelvin. These two type of isotherms 6 and 7 shows by non-wetting adsorbent and adsorbate system.